So we continue with our lecture on potential flows and primarily trying to see that how we can use superposition of potential flow solutions in order to understand flow around objects. So what we saw in the last lecture was that we started with a superposition of a uniform flow and a source. So once you superpose the two, qualitatively you would expect that the uniform flow will get deflected by the source, and the source also would not be able to actually move in all directions radially outwards. So that too would actually have streamlines bending due to the uniform flow. That's a qualitative picture. So when we went ahead and did this formally, we saw that there is a streamline pattern where you now have a stagnation point. So we identified the location of the stagnation point, and then finding out the equation for the streamline that passes through the stagnation point, because the value of the stream function is going to be a constant on a streamline. That's the definition of a stream function. And using that, so we had an algebra error in the end. So finally, until here we had this correctly, and then there was a sign issue. So this is the correct sign. So r is pi minus theta by sine theta. So as you can see, this particular function r starts off from 0, which means that it is when pi equals to theta, I basically start off, and as I keep moving into smaller and smaller theta, so as I go for smaller and smaller theta, eventually, so when theta equals to pi, this would go to a constant value which would be q by 2. So when theta approaches pi, then r would basically be the location which is q by 2 pi u. So the location of the stagnation point in x and y coordinate is minus q by 2 pi u comma 0. In r and theta, it is q by 2 pi u comma pi. So when theta approaches pi, r is equal to q by 2 pi u, and as theta goes, so this is the measurement of theta. So this is my theta. So as theta goes towards 0, you can see that the numerator remains finite for r, while the denominator goes to 0, which means that eventually this particular streamline is going to keep fanning out or keep becoming larger and larger. So this is what is known as flow past a half body. The reason why I am saying this flow past a half body, the blue line, which is also a streamline, is separating streamlines which is inside and those from outside. So if there was a fluid particle which was outside, it would never penetrate or come inside the blue line. So the blue line is kind of is acting like a boundary. So in many ways you can think of that if the blue line, which is a streamline, was replaced by an object, this exterior flow field would satisfy the no penetration boundary condition on this particular object, where the shape of the object is given by this particular equation. Then what we did next was we said, what if I have a source and a sink placed of equal strength but placed symmetrically either side of the origin. So now the source is going to expand out the uniform flow streamlines, whereas the sink is going to draw in the streamlines. So because of this exercise, now you have a flow pattern, or you have now a streamline which becomes a closed streamline. What was a half body streamline now actually closes on, and you get an oval, and this is known as a Rankine oval, where you have flow pattern that is outside this red line. The red line, I would remind you again, is a streamline, and there is a velocity profile inside which I have not sketched, but if you were to draw the velocity profile, this would look somewhat like a dipole. So you will have, this is a source, so the streamlines are going to radiate outward, and this is a sink, the streamlines are going to come in towards the sink. So if you view the flow field outside, any fluid particle that is on any of these blue streamlines will never end up entering into the red region. And on that particular red streamline, because it is a streamline, by definition there is no normal motion, so you can replace this with a body. You can say this is a solid object, and I am interested in potential flow past this solid object. So, when you are doing this, you are satisfying the boundary condition naturally, and you have obtained what is the velocity field that you have due to this particular combination of source and sink combination with uniform flow. So, this takes us to the part which is where we bring those sources and sinks close to each other. So, now the source and sink are going to coincide, and where they are coinciding, where the strength becomes also very large, such that, so this was where we said I have a source of plus q, I have a sink of minus q, the separation is epsilon, I will let epsilon go to 0, but then I will keep the strength of the source and sink times the distance to be fixed, and this is what gave us a dipole. So, now we will have a uniform flow and we will have a potential dipole. So, this has a potential that is u times x. I will consider this to be an imposed flow. So, I will put a infinity there, saying this is a stream that is coming from infinity, from left to going towards right, that is u infinity. And here I have a dipole which is lambda cosine theta by r square. So, lambda cosine theta by r square, one sec, was it, okay. So, this is lambda cosine theta by r, that is the dipole. So, you have a uniform flow which is u infinity x, and you have a potential dipole that is lambda cos theta by r. So, now you can start to imagine that when you have this uniform flow, when it approaches the potential dipole, again before you do a calculation, it is going to get deflected. There will be some deflection that you would have. So, what should the flow pattern actually look like for this particular problem? Now, we are not interested in doing some arbitrary superposition. Why are we doing this exercise in first place? The reason for doing this is we are going towards understanding how do we do flow past objects. So, our eventual attempt is we want to do potential flow past objects. Now, you could always solve this problem by considering a specific geometry, and then once you consider a specific geometry, you see all the solutions that are possible for potential flow and applying the boundary condition. Here we are trying to motivate it a little differently by saying that what does the flow feature look like when I am trying to combine some of these fundamental solutions. So, these are my building blocks. Uniform flow is one of those fundamental building blocks. The source is one of those building blocks. A sink, potential dipole, a point vortex, these are all building blocks which are basically going back to what are the series solutions of the Laplace equation. So, each of those terms in Laplace equation, those series solution, I can view them as building blocks, and I am using combination of those solutions to understand what should the flow feature look like. So, based on going through uniform flow plus a source, uniform flow plus a source plus sink. So, we looked at uniform flow plus a source, then we did uniform flow plus source and a sink, and now we are doing uniform flow plus a dipole. So, based on this, what we are trying to arrive at is seeing that if this is going to give us a flow field around a circular object. Now, this might appear a little arbitrary or more like guesswork, but in general you can rationalize this by thinking in terms of that I have my solutions. So, I wrote down the solution of del square phi. So, the solution of del square phi was a naught log r plus some b naught theta, then a summation over c n r n plus, or rather I think I had a n r n b n r to the power minus n plus c n. So, this multiplying cos n theta, and then c n r n plus d n r to the power minus n sin n theta. This is like a most general solution you have in terms of the circular harmonics. Now, if you say that I want to study flow past an object, you can start looking for which of these solutions combinations would all the terms in the series appear in your solution. So, we aren't going to take that approach. We are basically already aware of the fact that doing a uniform flow plus source and sink gives me flow past an oval shaped object. So, now if I were to bring the source and sink and fuse them and get a dipole, I am expecting this to actually give me flow past a domain which is circular in nature. So, instead of going through this kind of an approach, we are taking a shortcut by trying to infer from what we have seen as the velocity profile. But this is a more formal approach. In general, you will do this in a more formal setting when you are doing for any particular object. So, with that clarification done, now let us try to go back to doing the calculation. So, we will have u infinity x plus lambda cosine theta by r, that is my velocity profile. Now, I would work in cylindrical coordinate system. So, this is my velocity potential, which means my radial velocity is dou phi dou r, which is u infinity cosine theta plus lambda cosine theta minus 1 over r square, and u theta is 1 over r dou phi dou theta, which turns out to be minus u infinity sine theta minus lambda cosine minus lambda sine theta by r square. Okay. So, this is my velocity field that I have in my problem, where u infinity is an imposed flow and the strength of the dipole is something that is arbitrary. Now, I want to solve a specific problem. The problem I am interested in solving is I have a circular cylinder of radius a, and I want to find the velocity profile or the velocity disturbance that is created when there is a uniform flow going past that circular cylinder. This is a very classical problem, flow past an object, and the simplest flow past an object is when you have a circular cylinder. So, we want to study the two-dimensional potential flow problem here. This is as easy as it can be in terms of understanding what does an object do to an incoming stream. You have a uniform flow, and the uniform flow obviously cannot penetrate through the object. The object is a boundary of no penetration, no normal velocity. So, the boundary condition in this particular problem is at the surface of the cylinder. So, at r equals a, so if my origin is here at r equals a, the boundary condition we know from potential flow should only be the no penetration boundary condition, u dot n equals 0. Now, what is u dot n? It's a polar coordinate system, n is always radial. So, this implies that radial velocity should be 0, right? That is the boundary condition. I mean, because I have chosen a circular cross section, which is why the boundary condition is u r equals to 0. If I had chosen an elliptical cross section, it would be more complicated. It would be some combination of both u r and u theta. Finally, the boundary condition is no normal velocity. So, for circular cylinder, it's an easy in terms of geometry boundary condition, because it now is that you cannot have any radial velocity at r equals a. Okay. So, going back to what we just did, which was we looked at a combination of a uniform flow with a dipole that is of arbitrary strength. We do not know what is the strength of the dipole. So, when we work out what is u r, we found that u r actually gives me u infinity cosine theta minus lambda cosine theta by r square, and u theta gives me minus u infinity sine theta minus lambda sine theta by r square. These are the two velocity components that I have in my problem. So, now let us apply boundary condition. Boundary condition is UR is equal to 0 at R equals A. So, UR is 0 at R equals A. If I apply here, I get U infinity cosine theta minus lambda cosine theta by A square is equal to 0, which tells me that lambda should be U infinity A square. So, the dipole strength, which was arbitrary or unknown to begin with in the calculation, now gets fixed because we want the radial velocity to vanish exactly at R equals A. If you didn't enforce that, then the location where the radial velocity would have gone to 0, if you were doing this for an arbitrary dipole strength, then the location where UR would have gone to 0 would have been square root of lambda by U infinity, right. For any arbitrary lambda and arbitrary U infinity, there is going to be a circle at which you will have 0 radial velocity. If you let both of them be arbitrary, if you let both of them vary independently, you don't get to choose where the radial velocity goes to 0. If you want to choose where the radial velocity goes to 0 because you have an actual body in mind, you actually have a physical object in mind of a given radius, then the dipole strength is no longer arbitrary. The dipole strength gets fixed. You can only say I have a uniform flow U infinity, you know where the velocity should go to 0, and thus automatically the dipole strength gets fixed. So, now your U infinity and lambda, we have a relation. So, if I use that, I have U infinity cosine theta is 1 minus A square by R square. U theta would be minus U infinity sine theta 1 plus A square by R square. Now, this is the boundary condition which is on the surface of the circular cylinder. But there is one more boundary condition. The other boundary condition is the velocity field should approach U infinity as R tends to infinity. Far away from the circular cylinder, it should be the undisturbed uniform flow. You have a uniform flow that is impinging on an object. The object is obviously going to distort that uniform flow. You will no longer see a perfectly uniform flow near the object because the object is a no penetration boundary condition. Fluid cannot penetrate through the object. But if you were sufficiently far away from the object, the influence of the object is going to decay down, and you should get back the uniform flow in the limit of very large distances from the object. So, that is the second boundary condition. And now, if you check, if you take R going to infinity, UR approaches U infinity cosine theta and U theta approaches minus U infinity sine theta, which is nothing but Ux is approaching U infinity. Now, this is not a stroke of luck. It is not like we landed on a solution which automatically satisfies the boundary condition. We have chosen this carefully that the potential was a dipole. Now, you could have added other terms to this particular series. If you remember, this is part of a series solution. There are other circular harmonics that are there in this. So, if you were to add other parts of the series solution, what would happen? So, just for the sake of a quick check, you want to say that the solution should approach go to 0. So, let's take the argument of it going to 0. So, it should go to 0 at far distances. So, if it goes to 0, which means in the series solution, you can only take potential which will have decaying harmonics, right? Because if phi is growing at infinity algebraically, so if phi is some function that is r square, r cube, r to the power 4, if it is any function which is 2 or higher powers of r, automatically that rules out the possibility of getting a decaying velocity field. Because if phi had a form that was r square, this will give you a radial velocity. So, if phi goes as r square, ur will go as r. Now, that is not possible, right? Far away, we know that the velocity should go to a constant, which means the potential can only have three kinds of pieces. The potential can have dependence, that is with r. It can have dependence which are 1 over r and maybe higher powers of r. Now, r is already there. X is basically r cos theta. 1 over r is also there, right? Now, what is not here are terms like 1 over r square, 1 over r cube. Now, you can say they are decaying terms. Now, why can I not have 1 over r square, 1 over r cube kind of terms? So, if you were to have 1 over r square term, let us say hypothetically, you had a term here which was cosine 2 theta with some constant a2 that was added to the potential. What would be, now that satisfies the boundary condition at infinity, because a 1 over r square potential will give you a velocity field that will decay as 1 over r cube, because the radial velocity is dou phi dou r. So, if you have a potential that is a2 cosine 2 theta by r square, your ur would go as a2 cosine 2 theta minus 2 by r cube. So, that satisfies the boundary condition at infinity. Now, where is the problem? The problem is, if you were to supply the boundary condition at r equals a, then at r equals a, you will have a dependence here which is both depends on cosine theta. If you added one more term which was at 1 over r square or 1 over r square in the potential, you will get a term here which would be a cosine 2 theta kind of a term with some constant. Now, the boundary condition, what does the boundary condition say? The boundary condition says that ur is equal to 0 at r equals a, irrespective of the value of theta. Correct? That is what the boundary condition is, which means if that has to be true, then all the coefficients of cos theta, cos 2 theta, cos 3 theta should be 0. Now, the coefficient of cos theta going to 0 gives us the strength of the dipole, but the coefficient of cos 2 theta is exactly the strength of that term, and that has to go to 0. You will not be able to balance it with anything else. So, this is like doing it in a more formal and rigorous manner. I am just giving this in a more in a slight hand waving way, but you can do this rigorously. You can do this rigorously by saying that let us consider all the terms to be there, and very quickly you will figure out that all the terms either violate the boundary condition or they have to be 0 if you have to satisfy the boundary condition on the surface of the circular cylinder, or it will not be satisfying the boundary condition at infinity. So, this is basically how you do this in a more formal manner if you were doing a more complicated object. So, we will stick to what we are doing right now. So, we have now derived the velocity field for flow past a circular cylinder. Now, how does the flow look like? The flow, if you now were to sketch what the flow looks like, it will look like a streamline that is parallel to the x axis, and then the sphere will make it deflect. So, you will have what is very familiar in terms of what the flow profile will look like. So, you will have streamline patterns that appear of this kind. So, you are seeing a stationary object and you have flow past that stationary object. So, that uniform stream will come, it will deflect around the object and again converge and move further downstream. This is basically what the velocity profile looks like. Now, What about the tangential velocity? We never said anything about tangential velocity on the surface of the cylinder, because we are saying that the boundary condition is UR equals to 0. So, UR is U infinity cosine theta 1 minus a square by r square, and U theta is minus U infinity sine theta 1 plus a square by r square. Now, what is the value of U theta on the surface of the cylinder? UR is obviously 0. So, at r equals a, UR is equal to 0. That is the boundary condition. But what about the tangential velocity? So, if you put r equals a, you get that the tangential velocity is non-zero other than two specific locations. So, at theta equals to 0 and theta equals to pi, for r equals a, your total velocity field is 0, and these are what we call as stagnation points. So, I will sketch this once more. I will have a circular cylinder here. The stream is going to come, get deflected, the stream is going to come, get deflected. So, if you were to find U theta would obviously, so there are two stagnation points. There is one stagnation point here and there is one which is there. So, you have a forward stagnation point and you have a rear stagnation point. Now, theta is obviously being measured in this manner. So, the maximum value of U theta on the surface. So, if I label this as U theta surface, the maximum value is minus 2 U infinity, which occurs at theta equals to pi by 2 and 3 pi by 2. So, at this location, what is the direction of U theta? It is along x, right? At theta equals to pi by 2, U theta is nothing but Ux. So, the value here is 2 U infinity. U theta is minus 2 U infinity, which means Ux at that location is plus 2 U infinity. If you do the transformation from UR U theta to Ux, Ux would be plus U theta at theta equals to pi by 2. It would be UR cos theta minus U theta sin theta, and you would actually find that at theta equals to pi by 2, Ux will be plus 2 U infinity. So, now if I draw a line along the y axis perpendicular to the flow at theta equals to pi by 2, what would the velocity field be here far away? What should it be? U infinity, exactly. It should be U infinity. So, you can think of this that the velocity field is going to decrease from 2 U infinity to U infinity. So, there is a very fast tangential flow or flow in the x direction on the surface of the circular cylinder at theta equals to pi by 2. So, U theta obviously accelerates. So, this is 0 here, it is going to accelerate and achieve a maximum value. So, imagine you are crawling on the surface of the circular cylinder. So, a fluid particle which is sitting on the circular cylinder, as it tries to move, what is happening? As it tries to move, it is experiencing an accelerating flow. The radial velocity is anyway 0, there is nothing to think in terms of radial motion. But if you were sticking to the fluid surface, because we are doing potential flow, I am allowed to slip. So, as I am slipping on the cylinder surface, I start from the stagnation point S and, or let me call this S1, I start from the stagnation point S1 and I start to accelerate. I accelerate and achieve the maximum velocity to u infinity, and then I will start to decelerate. And this is an important point which you will come back to much later when we discuss boundary layers and separation. That why would there be a separation? When we finally start discussing about separation, I will bring this point back up where you will think of that the flow on the surface of a circular cylinder, the forward and the rear region have very different acceleration and deceleration mechanisms. And when you think of acceleration and deceleration mechanisms, you will also now start thinking in terms of variations of pressure. So, how do we do variation of pressure? How do we get pressure from this? Because all this picture that we have here, this is a picture purely of velocity, but we also need pressure. Without pressure, we can't move any forward and do anything meaningful out of this. So, what is our approach of getting pressure? We use Bernoulli equation. This is an irrotational flow, and we have also chosen a flow that is steady. So, I have a steady irrotational flow, which means I can use Bernoulli equation and write down P1 by rho gz1 plus half u1 square is P2 by rho gz2 plus half u2 square. Now, we are not looking at any elevation differences. There are no elevation differences in this problem. So, Z1 and Z2 are the same. So, I have now a relation involving pressure. So, I have P1 minus P2 by rho is half u2 square minus u1 square. And these points 1 and 2 can be anywhere in the flow. There is no restriction where you choose these points. You can choose these points to your liking, whatever you want. Nobody gets to tell you that you have to choose these points only on these specific lines or specific streamlines, etc. Potential flow, you get to choose wherever you want. So, what we will do, we will choose one of the points on the surface of the cylinder and the other point at infinity. So, I will choose P1 as on the surface and P2 is going to be at infinity. So, this is at r equals a and this is r being at infinity. Now, at r equals a, what is u1? u1 is the magnitude of the velocity. So, u1 is actually ur square u theta square. Now, on the surface of the cylinder, ur is not there. So, this is technically just the magnitude of the tangential velocity, which we worked out to be 2 u infinity sin theta, right. Now, what is u2? u2 is the velocity at infinity, which is the magnitude is u infinity. So, at infinite distances away from the cylinder, the velocity should just be u infinity, and the velocity on the surface of the cylinder should just be the tangential velocity, which is 2 u infinity sin theta. So, we are now more or less there to write down the surface pressure as Ps minus P infinity by rho half u2 is u infinity square minus 4 u infinity square sin square theta, right. Now, I can write this Ps minus P infinity by half rho u infinity square as 1 minus 4 sin square theta. Okay. This quantity is known as the pressure coefficient. Okay. So, now if you plot the pressure coefficient Cp as a function of theta, so when theta is equal to 0, Cp has a value of 1. And as you keep increasing your Cp, increasing your theta, Cp is going to attain a minima. The minima it is going to attain is at pi by 2. The point where the pressure coefficient is the lowest is going to be at pi by 2. So, which would be approximately around, so theta equals to pi by 2, that gives me around minus 3. So, I will have something like this. So, this is 0, this is pi by 2 and this would be pi. Now, you can see this point theta equals to 0 will lead to your pressure basically dropping as you go towards pi by 2. So, if you are moving along theta, which means you are, so theta if you define this way, if you are moving along theta, your pressure basically decreases and then it further starts to increase. So, there is an adverse nature in terms of your pressure variation, that between 0 to pi by 2 you are moving towards decreasing pressure gradient. Like if you define a quantity that is dou p dou theta, we know dou p dou theta on the surface of a circular cylinder, on the surface dou ps dou theta is negative in this half and it is positive in this half. This is an important point because we are going to come back to this particular point when we discuss separation, because now you have understood just from potential flow theory there is a distinction between the two halves of a circular cylinder in terms of how the variation of pressure is occurring. So, this is going back to the question we have had previously, that what is the utility of doing potential flow. So, you are seeing that you are getting clues regarding what is going to come in future. That if I were to tell you that look, the surface of a cylinder or surface of any object facing the flow and behind the flow, they are different. Now, you will say why are they different? Potential flow tells us that if you were to actually find the surface pressure, the pressure gradient, not the actual value of pressure, the surface pressure gradient, there is a favorable gradient region and there is an adverse pressure gradient region. At this point, there is no distinction between favorable and adverse because we don't know why they are any different. But in future, when you are going to learn about boundary layer and separation, this is going to be a clue, because you will immediately do a callback to what you learnt in potential flow and you will be able to say that what is happening in the two regions of Cp. Okay. So, this is where we have pressure calculation. So, as you saw that it got significantly simplified. Nowhere did we explicitly solve Euler's equation. We saw Laplace equation, which had nothing to do with momentum conservation. It was basically based on two constraints, incompressibility and irrotationality, with the boundary condition of no penetration. So, we use these constraints and the boundary condition to get the solution of velocity potential, and then we use Bernoulli, which was obtained from Euler in order to obtain pressure. So, we were actually able to do a calculation where we have never said anything about not doing a nonlinear calculation. We are not doing some very simple geometry. It is a circular cylinder in a uniform flow. It is quite complicated. If you think of, if you take a step back and think what you have here, the velocity field that you have obtained, the pressure solution that you have obtained, it's not a very, it's not a trivial calculation. But the ease of how we do things when you say it's potential or irrotational allows us to do this in quite simple terms. So, we don't stop exactly here, we still have one more thing to do. The last thing to do is find the force acting on the body. So, we need to compute what is the force that the body is going to experience. Now, how do I find the force acting on the body? If you remember, we computed that the surface force was sigma dot n integrated over the cross sectional area, right. So, this is our expression for the force that a body is experiencing. If you have a body in a fluid, the fluid surface which is attached to the body is transmitting the surface forces through the stress tensor, n being the normal on the body, and I am going to integrate this over the entire cross section of the body. Now, for us, the cross section is actually a perimeter, because the other dimension is coming out of the plane. It is a 2D object, which means that you have a third direction which is coming out. So, it is the surface of a cylinder. So, there is a z axis which is coming out. So, if I want to find the force per unit length, then I will be doing sigma dot n over the perimeter of this object, right. So, the perimeter of this particular object is just going to be a d theta, right. So, if you measure your theta and you say this is small d theta, this is a, so that perimeter is a d theta. The cross sectional area is a d theta L. Now, what is sigma dot n? Sigma, if you go back, you remember that it has a contribution from pressure and it has a contribution from, for a Newtonian fluid, it has a contribution from pressure and it has a contribution from the viscous term. Now, we are interested in an ideal fluid. So, the only contribution to the stress tensor is pressure, which means F per unit length is the surface integral of minus P n a d theta, theta going from 0 to 2 pi. Now, what is n? It is the normal, right. And what is it in Cartesian coordinate system? Cos theta, sin theta. If this is theta, then in terms of x cap and y cap, that is cos theta sin theta, which means the force that the body experiences in the x direction is minus 0 to 2 pi p cosine theta a d theta, and the force which is in the y direction is minus p sin theta a d theta. This is known as the drag and the lift. So, drag is basically along the direction of motion, lift is basically perpendicular to the direction of motion. Motion, or it could be uniform flow. Here the object is stationary and then there is a flow past the object. You could do the other way around, where you could be looking at a translating object in a quiescent fluid. Okay. So, now here I am trying to hold the object and there is a flow that is coming and going around that object. So, how much force do I need to apply in order for it to stay stationary? Now, that force will have a component along the direction of the flow and will have a component that is perpendicular to the flow. So, the one which is along the flow, or which is basically in the direction of the flow, is what we are calling as drag, and the one which is perpendicular to the flow is what we will call as lift. So, now you had your pressure expression So this is now on the surface, so I can just put Ps. So Ps minus P infinity half rho u infinity square is equal to 1 minus 4 sine square theta, which means Ps is P infinity half rho u infinity square 1 minus 4 sine square theta. So Ps is P infinity plus half rho u infinity square and then minus 2 rho u infinity square sine square theta. So for calculating the force per unit length in the x direction, I need to do 0 to 2 pi Ps cosine theta d theta, right? That's the force in the x direction. So if you substitute, you have minus a 0 to 2 pi, this entire bit I will just call as a constant c. So that's c minus 2 rho u infinity square sine square theta cosine theta d theta. So the first term is an integral which is cos theta d theta 0 to 2 pi, which is 0. If you had a constant pressure and you integrated over a closed loop, you are basically just going to get a 0 force. There will be no variation, there will be no force acting on the object. The second term is 0 to 2 pi sine square theta cos theta d theta. Now sine square theta cos theta, I can basically write it further as 1, so I could do it as 1 minus cos square theta cos theta, and then I have cos theta minus cos cube theta, and then I can write cos cube theta in terms of cos 3 theta and cos theta. So finally what I will have is that this entire thing will involve integrals over cos theta and cos 3 theta, and it will be 0. Or you could do it the other way around, you can say t is equal to sine square theta, in which case this integral will be an integral of t square dt, and that would basically again go out to be 0. So integral sine square theta cos theta will also go to 0, which is saying that fx is going to be 0. You can do the same set of algebra for fy, in which case you are going to now do an integral of very similar kind, but instead with sine theta, and this once again will give you contribution that will cancel out and go to 0. Not cancel out, but individually will be 0. So what you find here is from the drag and the lift calculation that your Fx and Fy, and thus your total force that the body is actually experiencing, is 0. Now this is a bit surprising, and this is where you start rethinking what you have done for potential flow. The reason why this is a bit surprising is you took a problem of flow past an object, and once you took that particular problem, you have asked the question that what would be the force that the object needs in order to be held stationary. And without doing any fluid mechanics, you know that that is non-zero. You dip your arm in a flowing stream, you will feel a force. The cross section of your arm, for purpose of a mathematical approximation, is a circular cylinder. So you are going to feel a force when you dip your hand into a flowing stream. You don't need to actually do any calculation to know this. You move your hand in air, you are going to feel some resistance. So the fact is that what you have obtained here You got a velocity profile, you got a pressure profile, you got a lot of these things, but eventually you come across something that is quite paradoxical. Paradoxical saying that force on a uniform flow past a this was a circular cylinder is 0. So, this is known as D'Alembert's paradox, that there is no drag. We have found the two component of force to be 0, but in next lecture what we will see is that even if this was an object that was of a different shape, or the object was doing other things like rotating, but still continues to actually have a uniform flow past it. So, if there is a uniform translation of any object, you will find that drag is 0, and that is basically what makes this as a key point where you need to revisit and think how you do this calculation. So, we will stop here.